Question I get asked all the time is, hey, Matt, I've got one of these. I've got a lithium battery and I'm out and about and it goes dead, but I've got a car. The car's got a charging system and I can get one of these, right? DC 12 volt from the car to power poles. Can I just plug my lithium battery into my car and charge it up? Well, the answer is you can, but you shouldn't. And for $20, you can turn it into a system that works well. So stick with me a couple of minutes. I'll run you through how this works. So in order to charge a battery, we got to take power from a power source and put it in the battery. And that means, first of all, that the voltage of our power source has got to be correct. If it's too high, we'll damage the battery or the protection circuit in the battery, or something about the battery will go wrong. If it's too low, we won't be able to push any power into the battery and we won't be charging. We'll just be space heating at best. Unfortunately, the voltage in an automotive electrical system is not a constant. It can range anywhere from the high 11s when the vehicle is off and the battery's not fully charged, all the way up to nearly 14.5 when the alternator is putting out full output. In any case, none of these voltages are typically appropriate for charging lithium batteries. The very, very typical 4S lithium iron phosphate battery, nominal 12.8 battery voltage. The battery itself sits at about 13.5, 13.6 when it's fully charged, and to get it there requires a charge voltage of 15, maybe 16 volts. That's what most commercial chargers are. Your vehicle charging system just never gets to that voltage, and so it's not going to be able to effectively charge most lithium chemistries. The other side of the equation is current. Current must flow into the battery for charge to flow into the battery, and this is where the tables turn. Your vehicle charging system is capable of delivering massive amounts of current, hundreds of amps in some cases, especially if you get into larger trucks and such. Meanwhile, your poor lithium battery, couple of 3, 4, 5 amps if you've got a decent sized battery. If you have a smaller one designed for a QRP rig, might only be designed to take 1, maybe 2 amps. Your vehicle charging system is capable of literally smoking the membranes in the inside of a lithium battery. But wait, how can that happen? We just got done saying the voltage is too low. Well, the voltage is too low when the vehicle is nominal voltage and the battery is nominal voltage. But again, if you just started the car, it might be 14 plus volts. And if your battery is really dead, it might be all the way down at 10. That's a recipe for the battery to draw all kinds of current, which the car is more than happy to deliver, only the battery's not going to be happy about taking it. Proper lithium chemistry chargers not only operate at the correct voltage to charge these chemistries, but they feature current limiting circuits. There's a maximum current that a lithium charger will output. And quite honestly, this is not new. The old lead acid battery chargers used to have an amp setting on them too. All batteries benefit from regulating their charge current. Too much charge current cooks off electrolytes, damages membranes, and otherwise lets the magic smoke out of your precious battery. All right, and some of you are going, yeah, we needed those regulated chargers for the old batteries because they were stupid. But lithium batteries have battery management systems built into them. Don't those boards handle making sure that none of these bad charging things happen? No, as a rule, they don't. The lowest of the low battery management systems will only cut off the charge current when the battery pack reaches its whatever target voltage is. But it doesn't do any charge current limiting. If you try to charge the battery with 50 amps and destroy it, the BMS will let you do that up until the battery is fully charged or melted, whichever comes first. Now, higher end battery management systems do have a little bit more charging sense. They'll do things like balancing, cutting off individual cells inside the pack when they're fully charged and letting the others come the rest of the way up, or temperature monitoring to make sure that your battery is not getting too hot or too cold to be charged properly. But no BMS that I've seen to date, certainly not one on any consumer grade lithium battery, has built-in charge current limiting. It is the responsibility of the charging circuit to provide the correct voltage and limited current to properly charge the battery. So while this problem sounds like it's got a bunch of moving parts, the good news is it's a very common problem. I mean, lithium batteries are everywhere these days. And so the circuitry needed to make sure that you have constant voltage constant current, proper charging for a lithium battery is readily available. You can get a 5-pack of the circuit boards on Amazon for 14 or 15 bucks, something like that, assuming that your charging needs are modest, a couple of amps. Now, in our case, since we're trying to work mobile, we have one additional challenge, and that's this fluctuating and altogether not high enough voltage produced by the car. Well, there's good news there too. That is another cheap and readily available circuit called a boost converter. This is a switch mode power supply sort of in reverse. It's stepping up the voltage instead of the traditional step down, and it works entirely on DC. But that's perfect. That's exactly what we need to take the anywhere from 11.8 to 14.5 volts and step it up to 15 and change to run our charging circuit. All right, enough of me yakking. Let's go over to the bench and I'll show you how this goes together.
Okay, guys, here is the first board we want to talk about. This is the charging circuit. This is designed specifically for charging lithium-ion chemistry batteries. And you can tell that because basically it has 2 potentiometers on it. This one limits the maximum output voltage that will be put to these terminals sort of regardless of what the load does. This second one sets the maximum output current that the board will deliver, kind of no matter what the load does. You'll see it called a CCCV, constant current, constant voltage charger, and it even has some indicator lights over here to let us know what's going on. So the first thing we got to do is we got to set the voltage and current that we want on this board. Typically from the factory, these potentiometers come set to Lord only knows what. So what I'm going to do, I'm going to set this thing down. I'm going to take my handy dandy screwdriver and I'm going to back both of these things way off. They're 10 turn pots, so I'll turn them 6 or 7 or 8 times, something like that, so that I know that the voltage and current settings are both set pretty much to their minimums. Now, you got to watch. I'm turning these counterclockwise to turn them down. That's sort of the logical way to do it. But on these Chinese manufactured boards, it's not always the case. Sometimes clockwise is less. All right, I'm going to connect up my power supply and I'm going to grab the leads from the black meter in the middle is the one that is set up to read voltage. So we'll clip that onto the output here. And I'm going to go ahead and I'm going to give this thing 18 volts of input. I want something higher than what I'm asking for on the output so I can set the regulation. This is a down regulator only. It won't pump the voltage up. And I'm going to limit the current output to 100 milliamps because this board with no load on it should draw next to nothing. If it starts trying to draw a couple of amps, the magic smoke is on its way out. Let's go ahead and turn the power on. And we see that the output voltage right now is 4.92 volts, and the green light is on the board. That's the board telling us, hey, your battery is charged, because there's basically no current flowing through here. That's how it can tell. So let's come in here to this right-hand potentiometer, and let's start cranking this bad boy up, until we get to the 15 volts that we want for charging our lithium iron phosphate chemistry batteries. It doesn't have to be exact. It's going to shift around on you a little bit anyway with temperature and humidity and phase of the moon and whatever. So there we go, 15 plus or minus volts output, limited regardless of what we put into it. All right, so now what I'm doing is I'm adding the second set of meter probes here. The second meter is set up to measure current, which basically means it's a short circuit. It's going to short the output of this board, but I still have the voltage probe set up so we can see what happens to the voltage. Now, obviously, if we're going to test the short circuit output, we need to be able to deliver some current to the board. So I'm going to crank this power supply up. And this is why you want to turn the potentiometer down before you try this thing, because 5 amps is the limit of current delivery for this board, and we'd rather not fry it while we're trying to calibrate it. So let's go ahead and hit the gas here. And what you can see is that the board indicates that the battery is charging because there's current flowing through the output leads. At the moment, there's 1.74 amps going through the output leads. And because it's nearly a dead short, it actually only takes 0.17 volts across the output terminals to drive that much current flow, which is why you only see 101 milliamps coming out of the power supply. It just doesn't take a lot of power to push current through a dead short. Anywho, let's come in here, let's find our second potentiometer, and let's start cranking this bad boy up, because what we really want is a charge current of closer to 3 amps. So let's go clockwise, a couple of turns here. And these 10-turn pots are obviously pretty fine in their control. So don't be surprised if it takes a good bit of cranking to get it where you want it to be. And again, you don't have to be super fussy about this. It's going to change a little bit when it gets hot or cold or whatever. Now you can see delivering 3 amps to the output voltage has of course gone up. We're at 0.33 volts and we're drawing 0.219 amps from the power supply. So now this board is calibrated into a dead short. It will deliver a maximum of 3 amps. If I disconnect the current meter, go back to just the voltage, if I can do that. There we go. You see that as soon as the current drops, the voltage regulation kicks in, and even though the power supply is still at 18 volts, we're delivering 15.0405, something like that. Once you, these things are a little bit dependent on each other. Once you set the current output, your voltage may wander, so you can go back and turn it down as I sit here and do what I told you not to do and fuss with it. All well and good. Our charging board is functioning. It's set up for 15 volts and 3 amps, but we're supplying it with an 18 volt power supply. And what we wanted to do was to do this in a car. This is supposed to be a mobile charging solution. Our input voltage isn't going to be 18 volts. It's going to be somewhere in that range of just under 12 to 14.4, 14 and a half, something like that. What do we do about that? Well, enter board number 2. This is our DC to DC boost converter. This is going to take an input voltage of something miscellaneous and step it up to whatever voltage we set, again, using this potentiometer on here. A couple of things about setting up these boards. In this particular case, this is an example of one where the potentiometer is backwards. Clockwise actually represents a lower voltage. So again, we're going to take the screwdriver and we're going to give this thing a couple of good twists in the lower voltage direction, just so that when we first turn it on, it's not maxed out. The other thing you got to watch is the polarity of the output is backwards from the polarity of the input here. So we're going to end up with our wires crossed on purpose. And the third thing is that these boards do not function at all without some sort of a load on them. You can't just plug this into the power supply and stick your voltmeter on here and expect to calibrate it, because it won't work without a load. Now, with our battery charging board all set up and ready to go, we could just use it as the load, but I happen to have some of these half-watt resistors just sitting around. I don't even know what value they are. Somebody who feels like figuring out the color code could put it in the comments. We're just going to stick these in here. It doesn't really matter what the load is, just that there is one. Okay, and I'm going to do a couple of things here. One, I'm going to turn this current down. I can't turn it all the way down to like 100 milliamps. This thing needs enough current to supply the load and charge these capacitors in order to get started. You'll see that it doesn't require anywhere near an amp to run the board, but if you set the power supply down to 100 milliamps or something, it'll never get started. And I'm going to turn the input down to 5 volts. That's the opposite of what we had for this board. This is a step-up converter, not a limiter. So we want the voltage nice and low, and we'll see what the output ends up being. Okay, I got my probes on the output voltage. I got my power supply hooked up internally, and it's turned down, hopefully. So let's go ahead and turn it on. And we can see that with 5 volts in, we're getting 12.21 volts out. I probably should have turned this a little bit more. If I turn it a little bit more clockwise, you see we could regulate this voltage output down even lower. However, that's not what we want. we want 15 volts out. So let's go ahead and turn this thing counterclockwise until we get ourselves up into the 15 volt range. Now, here's something interesting. We set up the charging circuit to limit to 15 volts out. Odds are there are losses in this circuit. In fact, not odds, it's a guaranteed. So we were feeding it with 18 volts from the power supply. We probably don't have to go all the way to 18, but we do have to go higher than exactly 15 on our voltage boost circuit. So if I can do this without disconnecting my meter probes, let's go to 15. Let's go to 15 and a half, and whatever over that ends up being is perfectly fine. Okay, and just to check, let's go ahead and set this thing up to 13.8 volts. That's the sort of nominal voltage for an automotive charging system, and make sure, yeah, we still have good regulation. This board is doing a lot less work, obviously, to pump the voltage up from 13.8 to 15.5, and you can see that in the current flow. With 13.8 volts in, we're only drawing 32 milliamps. If I turn this voltage down to 5 and change, back sort of where we were, the current has gone up to 72 milliamps. The conservation of energy still applies even in these buck and boost circuits. The power has to come from somewhere. To put 15 volts into whatever load this is X number of watts. We got to get that number of watts out of the power supply, and a lower voltage, that means more amps. So now we got the whole thing together. 13.8 volts at 5 amps is the most my power supply can do, is my simulation of the car. We're going into our step up converter, where we expect to go from 13.8 to 15.5 volts, into our charging circuit, which will limit the output from 15.5 down to 15, and or a maximum of 3 amps into the load. So let's go ahead and turn it on. And fortunately, no magic smoke. We see function light on the voltage converter, and we see the expected green light on the charging board, and our output of 14.9596, something like that volts. Again, if you want to be fussy about it, you can turn it up just a little bit, but realistically, it doesn't make any difference at all. And then when we add the current meter, effectively shorting the output, we go into charge mode on the board. We see the output voltage drops all the way to 0.23 volts because it's a dead short, and we see our 3 amperes flowing through the output circuit. We're delivering 3 amps to the load while only pulling 0.3 amps from the power supply. And you go, well, how can that possibly be? Well, remember, the conservation of energy is done in energy units, in this case, watts. So 13.8 volts times 0.3 amps is in the neighborhood of 4 watts. 3 amps times 0.25 volts is under 1. So we're actually only about 25% efficient in this case. We're pulling 4 watts from the power supply, and we're pushing, if we're lucky, 1 into the load. The rest of that is turning into heat in these boards. Let's take a look at a more reasonable scenario. I have my 3 ohm battery discharge resistor set plugged in here as the load. So the board is in charge mode, and we're current limited, 3 amps output, but it's taken 9.5 volts to push 3 amps through this load because it's not a dead short. That means we're delivering 28.5 watts to the resistors. In order to do that at 13.8 volts and we'll call it 7 amps, we're pulling just over 37 amps from the power supply. So obviously there's still some loss in these boards. There's going to be loss in any circuit like this, but it's not nearly as bad as the dead short condition. Hopefully your battery is never a dead short. And just so you know, this really is the limit for these boards. And as it is, if you wanted to do this with any regularity, you would probably have to get some heat sinks for these transistors and maybe even a fan, because this coil gets hotter than is comfortable in operation. The boost converter is the one that's really getting the hotter of the two. It's rated for 5 amps, and we're only drawing 2.7 from the power supply, but you can really hear this thing singing. Nothing about this circuit is RF quiet or AF quiet. There's nothing quiet about it in any stretch. So don't figure you're going to use this while you're operating a radio. But Suffice it to say, if you wanted to run these two boards at 3 amps charge current for any length of time, you're going to have some active cooling on here. If you drop the output current to, say, even 2 amps, it would go a long, long way to reducing the heat and probably the noise generated by this mess. Yeah, just for grins here, I turned the output current down to 2.5 amps delivery, and I'm checking the current flow between the boost converter and the charging circuit, and I'm getting 1.4 amps, which again, this board is rated for 5 amps, and I don't know whether that's 5 amps in or 5 amps out. Either way, it's drawing less than 2 and it's producing less than 2, but it is still singing quite the song, and this capacitor right here is way hotter than you wanted. So again, you have to seriously derate components like this. When you get these cheap boards from China, the specifications are under ideal conditions, like you have this thing submerged in oil or something. There's no way any of this stuff is going to be good for 5 amps or 75 watts of charging without a whole bunch of extra pieces to handle the heat.
I've played around a bit with this circuit, trying different output currents and looking at the temperatures, and it looks like 2 amps is really about the max for, I don't want to add any cooling to the circuit. At 2 amp output, the DC to DC converter is perfectly happy, and the charge circuit long term gets warm, but it's primarily the toroid and the final output capacitor. They're both components that are going to be perfectly okay running warm. There's no silicon in there. And speaking of current, this whole arrangement has a sort of an interesting behavior where if you attach the battery first and then plug it into the power supply, it draws gobs of current because it's trying to start the switch mode circuitry, charge up those capacitors, and at the same time deliver a lot of power to the final load. It puts them in sort of startup mode for a lot longer than if you plug the circuitry into the power first and then attach the battery later. I think that second way of doing it is a far better way to go. Now, if your charging requirements are much more substantial than an amp or 2, they do make larger versions of both of these circuits. Just be aware that even if you get a circuit that's capable of handling a lot more power, it's still going to make all of that heat. It just has the mechanism to get rid of it. So make sure your environmentals are good. Make sure you don't have it stuffed in a case somewhere where there's no air to move around. And make sure you've got it attached to the vehicle some way better than just plugged into the 12-volt DC socket. And since I know someone is going to ask, yes, you could be supplying the power to this entire thing using solar panels rather than something like a car. Solar panels have a very similar sort of behavior. As the sun comes and goes, the voltage wanders all over the place, and it has to be sort of regulated one direction and then back down the other to properly charge the battery with it. So as always, questions or comments, leave those down below. Mash some buttons while you're there so the poor starving folks at Google can afford to have their Maseratis fixed and hire a few more content sensors. In the meantime, you guys stay safe, and I'll see you out in the field with some freshly charged batteries.